All right, I think we're live. Fantastic. Okay, so this is a little bit of an impromptu lunch and learn, but hey, impromptu is what it's all about. So y'all have seen me stand up here and talk about, I think we talked about monoids last time, and I've just been lately on a big kick of trying to understand these type classes. We actually podcasted about it this morning. And so we're going to be, sharing more of that and really hopefully showing how you can take these techniques really are beneficial in any language that you happen to be operating in, and that you already use them. And we're just going to give a name to them so that, and some functionality so that you can then have to think less about them. So when you encounter one of these structures, be like, that's one of these structures. These are the things that I can do with it. So let's go ahead and start with, and then I've been working on this little JavaScript library to try and to try and capture them, it's certainly by no means unique, but I think it does have a pragmatic approach where it really is focused on the things that you can do with these things, and not just kind of navel gazing at the structures themselves. So without further ado, let's start talking about a semigroup. Semigroup's actually related to monoid, but it's is related to, oh wait, I need to share my screen, don't I? So a semigroup is we'll do, a semigroup is a thing that can be smashed together, it can be combined together, it can be appended together. So this can really be, there's lots of different types of semigroups that I've shown up here. So the top one is integers over addition. The second one are arrays, JavaScript arrays. We're going to be talking in the context of JavaScript here. And the third one are JavaScript objects. And so this append is kind of like, this plus operator. There's more than one way that you can combine integers, but this is just one. It's just an example. So I can take 5 and 5 and I can add them together. I can append them and I get 10. By the same token, I can take the array 1 and 2 and 3 and 4, and I can append them together or concat them together and get this 1, 2, 3, 4. So I'm just taking two values of a type and smushing them together and getting one value of the type. With a record, you can take, or a JavaScript object, you can take two objects that have a unique set of keys and values, and you smash them together and you get this object here over on the right that has both the W key and the Y key. And so in either case, the operations are completely different, but what's similar about the operation is I'm taking these two values of a type and I'm combining them together to yield one value. And so that's a semigroup, and we do this all the time, right? We add this, we know this operation as addition, we know this operation as concat, and we know this operation as assign, object.assign, right? It's kind of weird that there's 3 names for what amounts to the same operation. And it turns out that really, because it is the same operation, we can give it a single name, and that's append. So in my little JavaScript library, which I will go to right here. Oh, I'm not sharing this window, so I'll go ahead and do that real quick. Screen share. Let me go ahead and share my entire screen. Actually, I'll just share. Yeah, let me just share the entire screen. Okay. So I can go into this little library and start up node. And let's see, I'm going to, yeah. Is that better? Oops. Okay, one more. Okay, and then so I will say const append equals require. Okay, so I have this append function, right? It's one function, okay, but I can use it to, if I want to append two arrays. Let's see that example that we did there. And I'll do this one, 4, 5, and 6. And so it takes takes those two array values and creates them into one, right? I could have also said, 1, 2, 3 dot concat 4, 5, 6, and I would have gotten the same value. But by the same token, I can take, from this example, I can say append, wx, y, z. Oops. I can take these two objects. And I can append them together, and I get those two objects. So that's a semigroup, right? So what's interesting to note there is we have a single function that can operate against multiple types, and so you're really abstracting the operation and what it really means to append, and being able to use that as kind of the forefront of your thinking, as opposed to the opposite, which is I have this discrete value. Let me come up with a ad hoc list of operations for it. So we're really trying to generate some higher level abstractions. Okay, so the next one that I want to talk about is, are there any questions there?
What happens with your append function? What happens if you give it values of different types?
It will use the first type. So if I say append wx 1, 2, 3, it's gonna do this append. Right? So, whereas if I do it the other way around, so you can see it used all of the arrays as object property keys. And so I have a property called 0, a property called 1, a property called 2, which are the indices of the array. I could do it the other way around, and it will say 1, 2, 3. Actually, it just takes that object and just puts it into the, yeah. So yeah, it uses the first one. Now, in a statically typed language, that would actually be a compile error. Yeah. But I'm actually I'm determining the type class, or I'm determining the instance of the type class based on the arguments that you use. And some functions will take more than one argument that you need to look up the type class. But yeah, so it's using the first argument for a dispatch. So that's semigroup. So the next one that we're going to look at is Functor, and Functor is really got a great name. I've come to enjoy it. I think that when you're encountering these names, they're so bizarre and they're so opaque. It's like there's semigroup and monoid and functor and bifunctor and applicative monoidal functors, but it really approach it just as you're learning a weird language like Hungarian. These words have meanings. They're actually quite quotidian. Once the Hungarian word for celery I'm sure sounds very exotic and strange to us, but to a Hungarian, it's like it's celery. It's that crunchy stuff that you eat and the strings get in between your teeth. And it's quotidian means kind of run-of-the-mill, everyday, not something particularly special.
The quintessential.
It's it's nothing. It means, you know, very common. Quotidian is not a quotidian in terms of the lexicon. Quotidian is not. It's not a quotidian word.
It's a way for the elites
to reference the hoi polloi. But my greater point was that you just have to kind of parse this vocabulary as a separate vocabulary. But once you do, the concepts are actually quite simple, and you get used to them, and it's like, oh, okay. It's handy to be able to say things like celery and peanut butter and chair, but they're not, you know, they're not difficult concepts. And so one thing it helps me do, if a word is throwing you off, just say it like 20 times. Just say functor, 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 and then like you're just, you know.
You say it 3 times in a row. Does George Clinton?
Exactly. But what a functor is, don't try and deduce anything from the name. What a functor is, it is a structure that can be mapped over. And what that means is you can give it a function, and it can change the contents of what it has, but it doesn't change the fundamental structure. Okay, so that's maybe hard to discern from words. So let's look at an example. So one example of a functor is an array or a list, right? So functors have this concept of mapping. And so what you can do is you can take a function. In this case, I've taken a function which is ×2, and you're going to apply it to this list over here, and you get the result over here. And the key thing that makes this a functor is that the structure doesn't change. The values, so functors, you know, I like to think of them as containers or contexts, and the value inside the containers changes, but the container itself does not.
So the structure itself is the functor, not the operation.
The structure itself, yes, we would say has an instance of functor. Is an instance of functor. So in this case, array is a functor, in the sense that I can apply a function to it, and I can get the exact same structure. So in this case, the structure is just the fact that it has n elements, right? So here we have an array of 4, and we are going to have an array of 4 on the other side. Now the contents of that array of 4 are going to be different. So here I'm applying doubling, so I'm doing 2, I'm doing 4, I'm doing 6, I'm doing 8, right? And so this is, you know, I'm applying through this and map. That is the operation that defines a functor, right? And so we're familiar with map, right? Array.map is the instance of functor for array. I sense a question, Joe.
Oh no, I believe I understand it conceptually. Just trying to parse the sentences.
Right.
Array.map is the functor of array.
So it's the implementation, right?
Okay.
So a functor must define the map operation.
Okay.
And so a instance of a type class is where you provide the concrete implementation. So array.map is the actual implementation of the functor interface.
So functor itself is like an abstract.
Yes, so functor is a thing that can be mapped. So if we look, in fact, we can kind of cheat.
So we could say, instead of parsing that array, because it implements map, is now a functor.
Yes. So here's in this library, this is the declaration of the functor instance for array. So we're essentially given a function and an array, we call array map, right? So we're just going to lean on the JavaScript implementation of that. But that's that. I use that as the first example because that's, you know, we're all familiar. I mean, mapping arrays is something that we do every day, all the time, and that is a functor. Values change, structure does not. Values change, structure does not. That's all it means. So let's look at another functor, another instance of functor. So here is object. JavaScript object is also a functor, okay, where the values are there, but the keys stay the same. So in a JavaScript object, the structure that it provides is a set of keys, and then you're allowed to put values on those keys. So here I've got a function that's just kind of a one-off, and I say, hello world, hear me roar, and we're going to transform that into hello mom, hear me sing. And but the thing to recognize here is that the structure of the object does not change. Only the values are changing. Okay, and that's pretty cool. You can actually do a lot of the stuff that you do in JavaScript pretty easily. Have you ever done like object.keys.reduce blah 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 blah? Like, well, what you're really doing is you're mapping over that object functor. So let's have a look at that in practice. So let's see. We'll do. So we're going to require map. So here's this first example. We can map x to x times 2 over 1, 2, 3, 4. You see, we got that. And we can also say map. Let's do the same thing. Map the same function over this object, which is going to be like 1 is 1, 2 is 2. Okay. So this is actually an interesting. This is actually an interesting thing here. My implementation is lazy. So you can actually, so let's this will take a tiny little tangent. So let's say I've got, let's say my start is going to be x is 1, y is 2, and then I'm going to say let double equals. We'll say x goes to console.log double, and then that. Am I?
Oh, no, sorry.
You know, final print again.
So I can say let doubled equals map double start. And you see it doesn't actually do anything, and then I can say double.x. And it actually evaluates there. And it actually covers through, so I can say let
Or if you double the double.
if I double the double,
Would it be getter of getters?
you're saying map double.double. So if I do like this,
Yeah, like function double.
like this.
Yeah.
So if I say doubled, right. So yeah, it's super lazy. And you can even take, I can take doubled, and I can say, merged equals append z is like 0, like that. Oops. So append is actually also lazy. Most of these are lazy. Like that. And then if I say merged dot, like it doesn't merge.z, then it I guess I should have, yeah, merged dot x. Anyway, that's a nice little side tangent. But I didn't want to distract from the point that if I'm being able to map over an object in the same way that I can map over an array, and I'm doubling it takes the exact same set of keys. All it does is it applies that function to the value. And so that's really, really, really handy. Because we can conceptually, it's very simple for us to think about just operating on a single value at a time for these arrays and for these objects, which could be very complex. You know, I could have 10 properties in an object, but I really only want to think about the value of one at a time.
As an implementation question, could like these lazy values also be like cached with just like a single cache?
Yeah.
That way, like every time you call merged x,
yeah,
you call the double function twice in this case.
Yeah, they could be. That's an optimization that I haven't taken, but I mean, it absolutely should be, right? Because it's theoretically these are immutable, or they should be. So they're pure computations. They're maps off of one. So once I've actually expended the computational resources to realize the value, I should never have to do that again. So let's keep moving on. So I think, you know, another, and we're going to cover two things. One, how to declare your own like typecast, your own type class, and then the next thing is showing just what you can do, like how nice map can be. So I'm trying to think of. I want to make it not quite a contrived example, but let's have a look. We'll declare our own thing for a tree. So we want to map a tree, one tree into another tree. All right, we'll do the same doubling, right? But a tree, like an object, like an array, is just a container. It has values. And so we want to be able to transform those values without transforming the structure of the tree. So what we're going to do here is we're going to do like a tree example here. And we'll import Functor from okay, and then we're going to just make a tree class that's going to have like we can give it like some data and a list of children. Okay. And then what we'll do is we'll declare an instance of the functor type class. So we'll say functor instance tree. Okay. And now we need to define map for it. Okay. So what we'll do is we want to basically visit every single node in the tree, run the transform on the data of that node, and then visit the children. So this is, you know, I don't want to get too bogged down into the implementation, but the first thing we want to do is we want to say like, essentially the data for this node we're going to apply the function to this tree data. Okay, then we need to apply the transform for all the children. So we want to say the children is going to be, we want to map the children here. No, this is an array map, right? Because tree this is a list map because children is a list. We can make this a little bit more explicit. Say so for every child, what do we want to do? Well, we want to return so now every here, let me I need to import. So there's a lot of maps going on right here. But the key thing is we're going to map over the child, and for every child, we want to apply the same. And maybe this might be a little bit helpful. This is a child tree. Okay, so we're going to call the tree map. We're going to map that function over the child tree. Okay, so it's recursive, and then we're going to return a new tree, which has data and children. Does that make sense? We're just doing, this is a recursive process because it's a tree, but we map ourselves, then we map the children, right? And the first thing that a child does is it maps itself. And then it maps its children, and it maps its children, blah, 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 blah. Okay, so now we can actually go and we should be able to, from inside, now this is, it might take me a couple times to compile this. I wonder if this is going to be. I might actually have to add my. Yeah. I'm using ESM here. Let's see. So I'll just, let's see if we can require. You know what? I'm gonna have to. No. Okay, so I'll just quickly hook this in here. This is. Tree example. Okay, so we'll just restore it. Oops. This one, yeah. Cannot find module tree example. What did I do with it? Right. Oh, there it is.
Where is it living in the root or another?
It's living in the root.
Could you have to go up a level inside the source of that? Yeah, you have to go up a level. Yeah.
Oh, all right. You're right. Okay. Does not provide an export in Functor. Does it? You know what? I'm just going to do it. I'm just going to copy this. Probably got some order of operations thing. See if that works. Okay. Okay. So now I should be able to say let tree, new tree, and we'll make, let's try and reconstruct our example here. We had 1, 2, 3, so three trees. So the data of the first tree is 1. And the children is an array of a new tree with data 2 and a new tree with data 3. Okay, so there's our tree, right? So now if we've done it right, I should be able to just say map x. Oh yeah, do I need to, I do need to do that. Okay, if I've done this right, now I should be able to say map x, let's do our doubling function, x times 2 over the tree. You can see, and so it just double the things. But you see, hopefully you can see kind of the beauty now is we've identified this thing called a functor, which is like I can just take any functions, and all I need to think about is how to transform one value, and now I can transform all the values contained inside that structure. And so, but I get to use, but I'm thinking now, and just thinking in terms of map. Thinking in terms of the operation instead of the data structure. And so for me, it's like, makes me immediately think, okay, now I know about this thing called functor. What is a functor? Like, I didn't even know that when I started out, I didn't even know that trees were functors. But then it's like, okay, what else is a functor? And then I can map it, and now it's really powerful. So that is it. Hopefully you understand what a functor is, what a semigroup is, and maybe kind of the difference between type classes and JavaScript classes. Any questions?
Now, you've used the phrase type class a few times. Like, what precisely?
Oh,
How do you define type class?
yes. So, well, I don't know if I can precisely define a type class, but a type class defines a thing. It defines a set of operations that can be done on a thing. So here's an example. Let's look at the functor type class that I've. So basically what it does is it says, this might even help some of the terminology. So here's the type class. So it has a single function called map, okay? And so a map is an operation that can be applied to any functor. And so here is where I actually look up the instance. So you get, you give it a function and a functor. Here I actually look up the instance of functor for this value. So that's what this is. So when we talk about the instance of the type class, so this is the abstract map function that will work on arrays, it will work on objects, and now we'll work on,
right?
What's that?
Those are the instances.
Yeah, so what's happening in our tree thing is like when you call functor, it's actually going to look up, it's actually going to look up this instance. And so the object that gets returned is this thing. So this thing is what you're actually, This thing is the thing you're actually working with right here, this object. So I'm destructuring it to get the map out of it, method out of it. And then you kind of return the actual map. And so that's what, so this is a type class, the set of operations. The instance is the concrete implementations of those. Although there's some, like with foldable, which is one we haven't even talked about, where length is not, you don't actually have to specify the length of a foldable. Because all you really need to do is implement fold right and fold left, and then given fold right and fold left, I can or given one of those, I can infer the length function just from those. So does that
Yeah, somewhat. So I mean, you could have like an object or a structure. In fact, in most cases, will belong to multiple type classes.
yes. So like object. So here's the you can see here's the this is the instance of map of functor for object. If we look at let's look at the instance of semigroup for object. Okay, I use a little bit different methodology. It's a little bit weird. I'm actually, because the way you make append lazy is you actually just you get the properties. Like, so I mash the properties and then just create a new object with the properties mashed together so that it's lazy. But it's essentially, you can see that semigroup, there's the instance is to make it, what's the word I'm looking for? Oh, it's to make it lazy, but it's essentially object assign. Any other questions? No? Concerns? Does that seem straightforward? Does that make sense here? Like, it's definitely turning things around a little bit. It's kind of inverting. Usually the things that are polymorphic are the objects, and here the things that are polymorphic are the functions.
And like the grand scheme of things, what does that buy you, right? Maybe it's just that like I haven't fully inverted my thinking on it, but it seems like there could be places where this would be like a detriment potentially, right?
Yeah.
Things coming in, right? Like I don't know, it gets weird with like thinking about
You're almost being
types.
kind of
Well, so
loose with the
one
types.
thing,
Yeah.
like,
you're being loose with the types. So here's one thing. Like, let's say
it could be
let's say I want to map something, right? And I've got like let's say I want to map something, and I say like let's say I've got some integer, right? Or I'm duck typing something, and so I'm passing a bunch of different values, and I say one.map, x times 2, like that. Saying one.map is not a function. Here, if we were to do the other way around, we'd say map1 or map x times 2 over 1. Oh, that works. Weird. Yeah. Turn the number. Huh. Let's see. Hold on. Whoa. Really? I'm surprised that actually JavaScript connected those dots. Well, so this isn't a great example because object has functor. But if you had some operation, you would get like, this thing is not a method versus like, because I'm actually trying every time you do a map, it like tries to get the instance. It'll be like, there's no, this value you have is not an instance of functor. It cannot be mapped across versus some map is not a function. It's the same thing, but it's going to be a lot more descriptive because you've got, you're explicitly doing the lookup. I mean, so that's one advantage. The other advantage is you're grouping. Like these methods are related. Like there is a grouper. I can have array.map. I could implement object.map. I could implement whatever.map, but there's nothing to say that those things are related. Versus they are the instance of functor for that object.
So rather than being loose with types, you're just basically saying these types are also of this thing. Like instead of being loose with an object and array, you're saying objects and arrays are also functors.
Yes. Right. Whereas like duck typing, it's just like if it happens to have some random map method, then let's call it. It's also disambiguates. I could have different implementations of map depending on like I could have both. I mean, I could have two. I could have two separate type classes, both with a map function that it's called map, but depending on where I import it from, it's not going to be ambiguous. So you can have multiple. There's no reason that a single object or single JavaScript class can't instantiate multiple type classes, and those methods might overlap in their names. Like I might have, maybe let's say I'm going to get way in over my head, but let's say we've got like some, there's like 6 types of functors. Like there's a functor, there's a bifunctor, and there's a bunch of other stuff like that. Like let's say they all have a thing called map. If I import map from bifunctor versus I import map from functor, it's not ambiguous about which one I'm calling, right? Which one I'm using in this case. So I can have, again, polymorphism by operation, not by structure, data structure. Does that seem weird to you?
Oh, hell yeah. It's cool, though. So
it's pretty liberating.
So, all right, you mentioned functor, bifunctor. Like, all right, so when you're working with objects that are like kind of descend from each other, right?
Mm-hmm.
Can you do the same thing kind of here, right? Like I want a functor that is mostly a functor.
Yes.
But also
so
this or does this.
I haven't implemented that, but what you find is you come across in Haskell, right? Like anything that's applicative is a type class, right? And applicative types must be both a monoids and functors. So an array, right, is both a monoid and a functor. So it's also applicative. So when you're defining the applicative type class, you can basically refer to it as an applicative and a monoid, or a functor and a monoid. Does that make sense?
Yes.
Like, is that what you're talking about, inheritance? Like, so you can
That's
compose.
not quite what I was asking, I don't think. But that, I mean, that makes sense.
So you put type constraints on. To use applicative, for example, you say it must be both a functor and it must be a monoid. So if it's only a functor, then it's not a monoid. Then it's not applicative. It cannot be. So, and what would happen here is that, for like applicative, you're going to be using the monoidal methods. And so if you don't have an instance of monoid for that thing, when you do that lookup, it's going to fail and say, hey, this isn't a monoid. GTFO. Monoid or GTFO?
Did you really say Functor 20 times, like verbally?
No, but I did in my head.
Okay.
Really, just to like desensitize myself to the strangeness of it. It's really effective.
Have you translated it into Hungarian?
Yeah, what is Hungarian for celery? Do you know?
I don't know.
Maybe it's Functor.
Maybe it's Functor. That would be awesome. Okay, so there is an event thing. Any questions? Any questions from the web? Did anyone? Oh, we have 2 viewers. What's that?
One of them's me, and the other might be over.
Elric. All right. Alrighty. Bye to Will and Elric, or maybe someone else. Yep. And the future. Hello to the future. And goodbye to the future.
And if you were wondering what Functor is in Hungarian, it's Functorhaus.
There you go. All right. It's a wrap.